Maybe it's because I've been teaching C programming and C++ programming for a while, but I'm beginning to think that pointers aren't everybody's cup of tea. I have noticed that on the day I introduce pointers in CSC 111, there is a sort of palpable sense of dread that washes over the room. I don't feel too guilty admitting, frankly, though, that one of my favorite lectures to give in 111 is the one introducing pointers. There's just something fun about doing that. I don't know if it's specifically creating that fear of dread, although maybe that's a little bit fun. One of the reasons why students in 111 often find pointers to be pretty hideous, to be pretty overwhelming, is that pointers solve a lot of problems for us in the C language. In particular, the reason we often initially bring up pointers in a C course is that we need the ability to provide other parts of our program with access to our original data without having to make a copy of it. And pointers give us that functionality. And people find pointers are overwhelming because you get these hideous tracing questions on exams and you have to work with pointers. And I think it might be because pointers are, in a sense, overpowered for a lot of the uses we have for them. If it's just a matter of giving access to your original data, pointers actually provide a lot of functionality we don't need for that. And that's one of the reasons pointers can be so terrifying. And so this video introduces a feature of C++ that is in the same vein as pointers. It's a mirror image of one of the common use cases of a pointer. But it doesn't have one feature of pointers that makes pointers so horrifying in a lot of cases. So although you will likely discover that this feature is going to give you some amount of indigestion on midterms, I hope you go into it understanding that it is not nearly as bad as a raw pointer. It doesn't allow us some of the functionality that raw C pointers allow. Now, it's worth noting you are allowed to use C-style pointers in C++, but for most of this course, we are going to go out of our way to avoid doing that. We are going to need them eventually, but we're going to go out of our way to avoid them unless we actually need them. And so the first building block to replace pointers, that overpowered aspect of the language, is something called a reference. And I have two examples I want to talk about at first, and then we'll go through some tracing examples of watching what happens as we throw references around the program. References are critically important in C++ for a lot of different reasons. One of them is they provide a cleaner interface than pointers when you want to provide somebody else access to your original data, but also because it turns out, as I've implied in a few of the previous videos, copying stuff can become a bit of a problem after a while when you get to complicated enough C++. And therefore, we want to go out of our way to avoid making copies of things in a lot of cases. And so we need some way of passing around our original instead of making a copy. So let's go through this example. I'm going to run the code as it exists right now, and we'll discover that it is not the least bit exciting. So if reference is 1, prints out the value. I've got this variable x, and it just prints it out over and over again as I do these tasks. What I want to demonstrate is all the ways we can modify the variable x. So x starts at 100. I initialize x to have the value 100. And then later I use a regular assignment to refer to x by name and assign it the value 6. And we can see the first two print statements print 100 and then 6. The other two print statements do nothing interesting yet because we haven't written the code. I also want to just briefly sketch out, if I were tracing this code as I wrote it, what would be going on. So here's my scoping box for main. There we are. And here's the only variable that I have in this program right now, which is x. All right. And x begins on line 12 with the value 100, so I'm there. I then print it out. I get to line 16, and I modify the value of x to be 6. All right, so I have that, and then I'm stuck at this task here. Now, I'm going to introduce references with this terminology. I'm going to call this an alias. I don't want to really call this creating a variable y, although colloquially that is what I'm doing. I'm making a variable called y. I just want to illustrate that what I'm creating isn't really its own new thing. It's actually just a new name for an existing thing. So I can write something like this. So here's how I'd make a variable called y that happens to start off with the value of x. I could say int y equals x or int y initialized to x. But we know already that, of course, line 21 is making a brand new thing, a thing that would appear on my diagram. That is not what the prompt is asking. It is saying create an alias for the variable x. So I still want there to be only one variable in my program. I want it to be this box here. I just want it to have two names. So I want there to be a different way of referring to the same variable. And I use this notation. So int and then this symbol, an ampersand. And recall that if I were creating a pointer in C, I would use a star. So this should already be painting a picture that what I'm doing is somehow similar or related to a pointer. This is called a reference. Formally, I might read the type of y as int reference, or reference to int. The same way that if I were creating a pointer, so for example, if I made a pointer p, I could say p is a pointer to int. I could make p a pointer to x. You are allowed to write this in C++. You are allowed to use C-style pointers, but of course, if you remember anything from 111, it's that maybe we should avoid them if we can. So here I'm creating something of type integer reference, and I'm initializing it to this. And you'll recall a few videos ago when I talked about the laws of assignment statements, I had to use some legalese when I talked about when we make copies. And that was foreshadowing this. It turns out I'm not making a copy of anything here. What I'm actually doing is making a new name for an existing variable. So when I make a reference to something, what I'm really doing is attaching a new name to some existing thing, something that already exists somewhere in memory, somewhere on my diagram. When I initialize a reference, what I'm doing is not making a copy of this value. I am instead just indicating what I attach the name y to. What I'm saying here is that I'd like to create a reference y that will be the variable x. So to be clear, hopefully the diagram is making this obvious. I'm not creating a pointer to x. I'm not creating a variable that points to x or something. What I'm creating, this variable y, is x. Y and x are the same thing after line 21. As of line 22, anytime I want to refer to this box here, I can use the name x or I can use the name y. Let's prove that point by finishing what the task is asking for. So it says, use y to set the value of my variable x to 1,000. So I write this assignment statement, y equals 1,000. And if you use the diagram the way I'm doing it here, where I just write the new name under the box, we'd say y equals 1,000. Well, I guess y is this box, so that now equals 1,000. All right, so we'll save that and see what happens if I try to run it. We can see there it is. After that assignment statement on line 22, the value of x is indeed 1,000 because x is a name for this box here, just like y is a name for this box here. So again, the key distinction is unlike a pointer, which would be a separate thing. If I create a pointer, so you might recall from 111, you might create a pointer that looks like this. Here's my pointer. It's of type int star, and it contains an arrow pointing at this. And then later, it might contain an arrow pointing off somewhere else in the distance. And that's fine. The pointer is its own independent thing. I can modify it as I see fit. In this case, what I'm creating when I create y isn't a pointer. Y is x. Y is just another name for something. And one key thing to understand is once y has been created, it behaves exactly like the variable x. That's it. Anything I could use x for, I could use y for. I could write something like y++. I could, if I wanted to, make a pointer to y. I could do anything I could do with x. It behaves indistinguishably from x itself. And that means I am not allowed to redirect this reference later. Y is now a name for this box, and it will be forever. For the entire lifespan of the name y, it will refer to this box. Unlike a pointer, there's no way to make it point somewhere else later. And that should be reassuring, because we might recall one of the most annoying things about pointers in 111 was the fact that you could make them point somewhere else later in the program. All right, so the second task, the second introduction to references, is to create another alias for the same variable, this time using the auto keyword. And so I'm going to make another reference to x. This time I'm going to use auto to do that. So I'm going to create a variable called z, which is x. And I'm using the auto keyword here, but we might notice that because z is going to be another name for x, the type of z is sort of obvious. It has to be the same as the type that was already there. It has to be the type of x. So using auto ampersand is a way of creating a reference without worrying about the underlying type, even though obviously the compiler would have to know that. And then I will do what the prompt is asking and use z to assign to the value of x the value 999. You can see there it is. When I'm done, I guess I should update my diagram. When I'm done, all three of x, y, and z, being the same thing, contain the value 999. I want to do a couple of other quick notes here. So one of them is, if I don't put an ampersand on auto, by default, what's assumed by the use of the auto keyword is that I'm creating a new variable. So if I write it like this without an ampersand, what I'm actually doing is I'm actually creating a new variable called z. I'm creating a new variable called z whose initial value is the current value of x. So in that case, it would be, not sure why that pasted in. In that case, I'd have a variable called z of type int, which is obviously not what I want here. So in general, if you would like to create a reference to something, to create a new name for an existing thing, you should find yourself using an ampersand somewhere in the name of the type of the variable. So auto ampersand or int ampersand. So I'll run that just to make sure we're back where we started. I guess I should put z back on my diagram. And then I also want to observe a couple of other points. While we should go out of our way to use uniform initialization, and uniform initialization has been a thing for many years, it turns out that you will often see references getting created by this notation. This is an initialization notation, and this is the reason I had to use legalese when I was talking about the second law of assignment statements. So I'm going to run this with this modification to show that the actual effect is exactly the same. And this is a bit of a tough one. This is annoying. I wish we didn't have this option so that the initialization syntax would be more obvious. When you create a variable which is a reference, you may set what it refers to using an equal sign or uniform initialization. Only on the line where you create the reference variable, so the name y or the name z, are you allowed to set what it refers to. And so in this case, if I write int ampersand y equals x, it has exactly the same effect as what I already had, which is it creates a name y that refers to the existing variable x. I can never make y refer to anything else afterwards. Now, this is confusing because it does make the equal sign appear to have two different meanings, which is why I like using uniform initialization. This is one of the problems that uniform initialization solved in the language. It makes it much more obvious. Here I'm creating the reference, and here I'm just using a name, the same way I would use any other name. I'm assigning a value to a variable. So in both these cases, though, what I was doing was creating a new name for an existing variable. Now, how is that useful for anything? I mean, that's the obvious question that I've gotten after years of teaching 116. Typically, after going through an example like this, that's the first question I get is, why would we care? Why do we want the ability to refer to a variable by more than one name? And the answer is, well, actually, in this controlled setting, we don't. It's sort of ridiculous. Inside of main, I can just use the name x. Why would I care that I can also call it y and z? Well, okay, we're taking small steps here. First, I wanted to prove that we can create references. The reason that we need them usually is because I want to pass them around the program. I want a function to end up with a reference to something in main, for example. And of course, in that case, because we know the function wouldn't otherwise have access to my original data, it is important that I have the ability to do that. So I'm going to show off an example of that in a minute. So here I've got a brief example. I'm going to sort of pseudo-trace this, I guess, as I go. We'll try compiling and just compile this example before we go any further. So here I have a function main, and I have two other functions, f and g. And you'll notice that f accepts its argument x by value. So from here on in, if we don't see an ampersand in the type of something, of an argument, we're accepting the argument by value. If I see an ampersand in the type, the argument is being accepted by reference. So when I initialize the argument that gets passed into G, it is going to be the original thing that was passed in, not a copy. So this is similar to what might happen if you passed in a pointer in C. One difference, though, is that when you use the resulting variable, so the resulting name x, you use it as if it were the original. You don't give it special treatment like you would with a pointer. And we'll notice that that's really helpful later in the course for things like what happens if I want to pass a vector by reference. If I use pointers to vectors, I have to worry about all sorts of messy notation, whereas if I pass it by reference, I use it as if it was the original, which I think is much cleaner, especially in a language like C++. So let's trace through this quickly. So I'm going to create a box for main. And I guess I'll have to put my output somewhere. So I'll put it down in the output window, but I'll draw it in. So here's my output. In main, I create a variable whose name is going to be z, and it's an int, and it's got an initial value of 0, and then I print it out. The first piece of output is z equals 0. And somehow today I've decided my z's are too rounded. There we go. Z equals 0. And then on line 21, I call the function f. So I'm going to add f. I mean, regardless of whether I'm using references or not, I have to add f to my diagram. There it is. F takes one argument, and its name is going to be x. And it's an int. And x is accepted by value. That means that x is going to be its own variable in the scope of f. It's going to be something different. And what I pass in will be a copy. In particular, what am I passing in on line 21? Well, I'm passing in the number 0. So x, when I call the function f, is going to get the value 0. If I now execute f, we'll notice it's the usual sort of red herring, which is testing our knowledge of the second law of assignment statements, which is on line 11, x equals x plus 6. Okay, so 0 plus 6 is 6. I take that value and I assign it back into x. In the scope of f, x is this thing. So I assign 6 to x, and then the function ends. Okay, so of course then that whole operation just sort of went to waste. I now destroy the scope for f, there it goes, and of course that value of x that I just computed is now useless, and it's gone. All right, so this is what we're used to. We are used to this way of calling functions from C. Whenever I call a function, I am passing my arguments by value. If I want to give somebody access to my originals, I pass in a pointer. Then a copy of the pointer gets passed, but I can follow that pointer to get to my original data. And so when I get down to line 22, I print out z equals, well, in main, z is still equal to 0. Okay, and then I get to line 24. And here's where something new happens. So on line 24, this is I'm passing an argument by reference. So on line 24, G is accepting one argument of type int. Okay, but unlike the argument that was accepted by F, the argument that G is accepting is the original. So G is not creating its own data here. G wants one of my original pieces of data. What I'm really saying is when I pass in Z, I'm allowing G to create a new name for the thing in main that's called Z. And in G, that'll be the name X. So how do I draw that out? I've spent a while trying to figure this out, like what a good diagramming technique for this is. How about this one? This is the one I used in I came up with this. I actually made this up during a lecture in 2021, but it just seemed to work. What I'll do is I will color in the box that I write in G. Because we need to know that there is a name in G called X. It's in the scope of G. The name X only exists inside of G. So it's important that there be something on the diagram for G. I'm going to color the box in and then direct the box, sort of like a pointer, up to point into main. Now, the difference is, unlike a pointer, the box can never be changed. So as you might recall if you've seen the videos for 111 that of me tracing through pointers, is that of course a pointer is a regular variable. I can modify what it points to whenever I want. That's important. That's one of the defining characteristics of pointers. That is not a characteristic of a reference. When I start G, X is now a name for this thing in main called Z. And X will forever be a name for that thing in main called Z, forever. And so I want some way of indicating that I may not change what it points to. And so I've used this. I shade the box in. It also helps me remember that when I set X to a value, what I'm really setting, X is actually this thing. When I use the name X in G, I'm referring to this thing in main. So coloring in the box makes it less likely I'm going to make a mistake there. Okay, so I've set up my call to G, and now I can run line 14. Okay, so we'll evaluate this like any other assignment statement, so we'll cover the left. What is X plus 10? Okay, in this scope, X is this thing. Okay, so what's the value of X? Well, it's 0. Okay, what's 0 plus 10? It's 10. Okay, so 0 plus 10. This whole thing over here ends up evaluating to 10. Where do I stick the 10? Okay, well, it says X equals. So what I'm going to do is I'm going to assign the number 10 to whatever is called X in this scope. Well, in this scope, again, X is that thing. And so I assign 10 to this. Because the box is colored in, hopefully that's clear to me that that it's a reference and that I have to go find what it really refers to and set that to 10. All right, and then G ends. And so we'll destroy the scope for G. And the name X is now gone, and I head back into main, and I'm now at the end of line 24, and so I hit line 25. And line 25 says print out the value of Z. So I print out Z equals 10. Whoops, and I typed a couple of X's there by accident. And then I head down to line number 27. And here I am creating, in the scope of main, I am creating a new reference. So it says create a reference to Z and name that W. So in the scope of main, what I've done is I've made up a new name for my variable Z, which as we saw in the previous example, I am definitely allowed to do. And then I call G again. So I'll make up a box for G. And I pass in W. Okay, so G is going to have something in its scope called X, and it's going to be something of type int. But X is a reference, so G doesn't actually have its own data. Instead, G is borrowing somebody else's original. What did I pass in? Well, I passed in W. In the scope of main, W refers to this box here. That means that what I'm passing in is this box here. So X is again going to refer to this. Notice that once I created the reference W, I can use it anywhere I would use the name Z. It's valid because they're both just names for this box here. Okay, so now I'm ready to execute G again, so I say X equals X plus 10. So of course this is, when I refer to X in G, I'm referring to this thing. So this was 10, now it's equal to 20. And then I've pasted in the letter W. My screen drawing isn't cooperating very much today. So I've put the value 20 inside of this box, and then G can end, so I'll go and erase it and hope the screen drawing can keep up. And so the scope of G is now gone, and then I get to line number 29 and I print out Z equals 20. So I've traced some code that uses references to allow a function to have access to original data stored elsewhere. Notice one of the nice things about references, because we can never change them, we can never change what X refers to after it's created, there's no need for special notation like there is with pointers, where we have to differentiate, am I modifying the pointer or what it points to? In this case, once X exists, I can just use it as if it were the original. It behaves exactly like the original does. And so I can use it without having to worry about there being different behavior in the function where the data is actually created versus a function where access is provided from outside. Now to complete the example, we'll actually run this and see whether I was on the right track with the output. And there it is, Z equals 0 twice, and then Z equals 10, and then Z equals 20. And we'll find that the most common use case you probably had for pointers in 111 was being able to provide access to original data to scopes outside where that data was created. You can now use references for that. And so there's no need to bring in pointers for that purpose. And we'll find that although it takes some getting used to, references are, I think, way more convenient for that purpose than pointers are.